Okay, so we've checked for normality in the variables and also for univariate outliers. Let's look at the other assumptions and also conduct our standard multiple regression. So we go to analyze, we go to regression, and we go to linear. And then now my dependent variable is exam score. And my predictors are hours spent revising and the anxiety that is felt, or whatever our measure of anxiety is, and pull that over to the dependence variable. Now if we click on statistics, let's leave the estimates there ticked. Let's tick confidence intervals. Let's leave model fit there and also tick descriptives. We're also interested in the case-wise diagnostics, and we're interested in outliers, anything more than 3 standard deviations. Press continue. And what about plots? Well, what we want to do is we're interested in here of Z presid and Z resid. So let's move Z presid into the X category and Z resid into the Y category. So what this linear regression of the plots does is it graphs the standardized residuals, which is Z resid, against the standardized predicted scores, which is Z resid. And then also let's choose the normal probability plot. So what this information is going to be used for is it's going to assess whether there's normality, linearity, and homoscedasticity amongst the residuals. Press continue. Now I'll go to save, and what we're interested in here is a Mahalanobis distance. That's going to tell us whether we've got any multivariate outliers or not. Press continue, and let's have a look at options. We'll just leave our standard options there, and don't worry about Bootstrap, and pressing OK.
For this data, R is equal to 0.839. And this value represents a multiple correlation between the criterion variable and the set of predictor variables in the model. And this is usually overlooked in favour of R squared. So the R squared indicates proportion of variance in the criterion variable that can be accounted for by the combination of predictor variables. So here 70.3% of the variance in the exam score can be explained by the variance in the hours spent revising or hours spent studying and the variance in anxiety levels of the students. So what this means is that nearly 30% of the variance in exam scores cannot be explained by the model. Then you've got the adjusted R squared, which is the estimate of the R squared in the population. Now the R squared is biased upwards, particularly in small samples, therefore the adjusted R squared is sometimes used. And then there's a standard error in the estimate. And this is a standard error of around the predicted criterion scores, or around the predicted dependent variable scores. Now we're doing a multiple regression because we want to be able to predict exam scores. Now one way to predict exam scores is just to give people the mean exam score. So this ANOVA table, it asks the question, does the model predict better than simply using a mean exam score as my best guess? So this table tells us whether the regression model is significantly better at predicting exam scores than if we use the mean value of exam scores as our best guess. So the most important part of this table is the F ratio, which is calculated by dividing the mean square of the regression by the mean square of the residual and the associated significance value. So here, for these data, the F ratio is 20.134. And since the sig value is less than 0.05, so in this case it's less than actually 0.01, then we can conclude that our regression model results in significantly better prediction in exam scores than if we use the mean exam scores, or the mean value of exam scores, as our best guess. So in short, the regression model overall predicts exam scores significantly better. Now, however, what the ANOVA table doesn't tell us is it doesn't tell us the individual contribution of the variables in the model. So as a result, we need to look at the coefficients table. So the B value for the constant is the y-intercept. So from the table we can say that the constant is 14.068. 14.068. And this can be interpreted as meaning that when a person doesn't study at all and their anxiety scores are 0, so in whatever anxiety measure you're using in the study. So in other words, when X1 and X2 are 0, the model predicts that you're going to get an exam score of 14.068. We can also read off the value for B1 and B2 from the table. It's 1.066 for the coefficient of hours spent revising, which is B1, and 105 for anxiety, which is a coefficient for B2, or coefficient for anxiety, which is otherwise known as B2. So these values indicate the individual contribution of each predictor to the model. So the B values tell us something about the relationship between exam scores and each predictor. So the two predictors have positive B values, indicating positive relationships. So as hours spent revising increases, exam scores increase. As anxiety increases, surprisingly, so do exam scores. So the B values tell us but the B values tell us more than this. They also tell us the degree each predictor affects the outcome if the effects of all other predictors are held constant. So hours spent revising, that's B equals 1.066. So for each extra hour you spend revising, exam scores will increase by 1.066 marks. Or what about anxiety with a B value of 0.105? So as anxiety increases by 1 unit on whatever anxiety measure you use, then your exam scores increase by 0.105 marks. Now we can also see in this model that hours spent revising is a significant predictor of exam scores. So the t-test tells us whether the B value in the first column of the coefficients table is different from 0. SPSS provides the exact probability that the observed value of t would occur if the value of B in the population were 0. So if the observed significance is less than 0.05, then the result reflects a genuine effect. Here we can see that hours spent revising has a significant effect on exam scores, as the sig value is less than 0.05. So hours spent revising is a significant predictor of exam scores. We can also say that the constant and the coefficient for anxiety, B2, are not significantly different from 0. In other words, the constant and anxiety of the student are not significant predictors of exam scores. However, these significance tests are only accurate if the assumptions of multiple regression are met. For example, or in our example, I've used 20 participants, and as such it's not the largest sample size in the world, and it's not really enough to provide reliable tests of significance of the predictors. In other words, the lack of sample size casts doubt on my conclusions. Now let's look at some more assumptions. What about multicollinearity? A natural starting point is to look at the simple correlations between predictors. So if you've got two predictors, then this is sufficient to detect problems. So the correlation matrix is sufficient to detect problems with collinearity or multiple collinearity. So if the simple correlation between the two predictors is 0, then there's no real problem. However, that doesn't really happen too often. If the correlation is low, then collinearity is probably just a minor nuisance, but will reduce the statistical power, meaning that you're less likely to be able to detect an effect, and that effect will be measured less accurately. A larger correlation indicates a more serious problem. Typically, correlation amongst the predictors of more than 0.90 is a problem. So working out how severe the problem is or not, well, it's not that easy, and it's generally a good idea to use a collinearity statistic such as tolerance or variance inflation factor for this purpose, but this is not part of this lecture or part of this course. So we can see here that we probably don't have multicollinearity, as the correlation between predictors is not above 0.90. Now, univariate outliers are those with extreme values on a particular variable, and they can be identified graphically with box plots and confirmed with z-scores. Now, multivariate outliers, however, are those cases that have unusual combinations of values across one or more or two or more predictor variables. So they can be detected by the Mahalanobis distance. Now, we request a Mahalanobis distance for each case if the Mahalanobis distance value is greater than or equal to the critical value of the chi-squared distribution for the degrees of freedom equal to 2, which is the number of predictors in our model, and alpha level less than 0.001, then we have multivariate outliers. So the critical chi value I looked up, the critical chi value for degrees of freedom 2 at an alpha level of 0.001 is 13.816. Now, since the highest Mahalanobis distance is 5.99, which is less than the value of 13.816, we need not be concerned with multivariate outliers. Now, the normal PP plot or probability plot of the regression standardized residuals can be used to assess the assumption of normality of residuals. So if the points cluster reasonably tightly along the diagonal line, as you can see here, then the residuals are normally distributed. Now here you might also have nonlinear residuals. So the residuals show a quadratic pattern, possibly because of the nonlinear relationship. Sometimes a variable transformed will eliminate this bias. Then there's heteroscedastic. You can see here it's small to the left, the deviation or the variability is small at the left of the plot and large to the right. So the residuals are heteroscedastic. And then you've got nonlinear and heteroscedastic. So the pattern here is quadratic. Then you've got unbiased and homoscedastic, which is great, that's what we want. And the residuals average to 0 in each thin vertical strip, and the standard deviation is the same across the plot. So we've reviewed the assumptions of the multiple regression. I've talked about each of the tables in detail and what they actually mean. Now I'd ask you to look at your text and look to see how you may write up a standard multiple regression.